Hello everyone. Very good evening. I hope I'm audible and visible. Yeah, okay. Thank you. So let's wait for 5 to 10 minutes so that everyone can able to join this session. Okay. Yeah, okay, let's start the session. Hello everyone, my name is Pooja Verma and PMRS Research Scholar from IIT Kharagpur. And instructor for this course is Professor Shantanu Chattopadhyay from Electrical and Electronics Engineering Department, IIT Kharagpur. This is a week 6 live interactive session on digital circuits. You can use the chat box for asking and interacting, or otherwise you can mute yourself and ask your questions or doubts. Okay, so these are the some topics which have been covered for this week lectures. So I hope all of you have gone through this week video lecture. So the topics are demultiplexers, buffers, programmable logic array that is called PLA also, sequential circuits. In sequential circuits, there are two types of synchronous sequential circuits and asynchronous sequential circuits. And then latches, there are four types of latches: SR, D latches, JK latch, T latch. And then come to the flip-flops. There are also four types of flip-flops: SR, set or reset flip-flops, T flip-flops that is also called toggle, D flip-flops, or we can say that delay flip-flops or JK flip-flops. Okay, and then conversion of between the flip-flops. That topic has been started but not completed. That we carry out in the next week also. Okay, so let's start the some question. Okay, so question number one is a combinational logic circuit. Option A must contain flip-flops. Option B may contain flip-flops, or option C does not contain flip-flops, or option D contains latches. Yeah, option C is correct. So, can you let me know what is a combinational logic circuits or sequential circuits? Yeah, option C is the correct answer. Does not contain flip-flops. Combinational logic circuits are the circuits which cannot store the bit. It does not have memory. Okay. Yeah, it depends on the present input. Does not depend on the past input. So combination. What are the examples of the combination logic circuits? Yeah, gates, adders, subtractors, multiplexers, demultiplexers. Yeah, correct, correct. Encoder, decoder. Yeah. Thank you for your. Yeah, correct. So, so combinational logic circuit does not contain a flip-flop. Okay, option C is the correct answer for this question. So this is a description of the previous question. So already all of you know that what is a combination logic circuit and sequential circuit. So I'm describing here once again. So combination logic circuits are the circuits which depends on their present input, does not depends on the past input or past state. So it does not have no memory. It does not have a memory. So it is also a no memory element to store the past output. So this is a combinational circuit. So these are the inputs and we will get the output. Okay, but in the sequential circuit, the output depends on not only the present inputs but also the previous state of the output, and that's why it has a memory element. Okay, so the memory element is connected as a feedback so that it can store the output, okay, and give it to the input. So this is the sequential circuit. Now next, a flip-flop has two outputs which are option A always 0, option B is always 1, option C always complementary, or option D both outputs are same. Yeah, yeah, option C is the correct answer. Always complementary. So this is a basic structure of a flip-flop which contains inputs and outputs, where inputs have two and outputs also have one is Q and another one is a Q dash. Okay, so basically flip-flop is a basic digital memory circuit and it is also known as a bistable multivibrator because it stores two outputs. Okay, it has a two stable states. That's why it is called bistable multivibrator, or you can say bistable. Okay, so which can store used to store the binary information either in form of 0 or 1, but it can store only one bit of data. Okay, so in the flip flop the outputs we are getting the q and q dash always in complementary. For example, if we are getting q at like 1, then the output q dash will be always 0, and if the output is 0, then q dash will be the 1. So the two outputs which are always in complementary. Okay, option C is the correct answer. Okay, moving to the next question. Next question is, a flip-flop can be designed using a NAND gate, or option B is NOR gate, option C basic gates such as AND or and NOT gate, or option D is any of the above. So would you like to answer this question? Yeah, option D is correct, but most of the flip-flops always designed using NAND and NOR gate. We can use AND or and NOT gate also. We are using while designing the flip-flops because, for example, while we are designing in convergence D to T, JK to D, JK to T, then we will use NOT gate and other gates also. Okay, so all the mostly we use the NAND or NOR gate while designing the flip-flop, but we can use the basic gate also for designing a flip-flops. So, or any of the above. From any of the above, we can design the flip-flop. So, that's right. Option D is correct. Okay, so moving to the next question. Which of the following combination is not allowed in SR flip-flop? So, option A, S is equal to 0, R is equal to 0. Option B, S and R are 1. Option C, S is 1 and R is 0. Or option D, S and R S is 0 and R is 1. So which of the following combination is not allowed in SR flip-flop? Yeah, option B is correct, but why? The reason is it has a set input and a reset input, okay? Two inputs in the SR flip-flop. Already we know that we have two input S and R. This is the clock, and two output Q and Q dash. We can design using a NOR gate or NAND gate. So when S is set as an active, the output would be high. If you have gone the truth table of the SR flip-flop, so we can see that if input S and R both are 0, 0, there is no change in the output. Okay, if both are 0, 0. And if S is 0 and R is equal to 1, so R is equal to 1, then it is going to the reset, or we can say also 0. Okay, if S is 1 and R is 0, then it is set, and it is also set is 1. and when both S and R is 1, it has gone into the invalid state. Okay, because uh, when both are 1, then both outputs gone to a 0 0. So that is not defined. It must be complementary of one output. So it has gone to the both 0. That's why it is called an invalid state. And this problem has been solved by JK flip-flop. This is a limitation of SR flip-flop, which the limitation has been done using a JK flip-flop. Okay. So this is a truth table of a SR flip-flop. Okay. So when both S and R is 1, then it has one invalid state. So that is called also not allowed in SR flip-flop. Okay, option B is the correct answer. So yeah, next one. The following circuit implements this circuit, what it is implementing. Can anyone tell me? D flip-flop with enable input T, or it is implementing JK flip-flop. Option C is T flip-flop or T type. The following circuit, what it is implementing. So let's check what it is. It is a first we will see in the input what is going to the input, that is T. It is a symbol of XOR gate. T XOR Q. Here is going to T XOR Q. Okay, input is T XOR Q. So what is the truth table for T flip flop? Or anyone can tell me what is the characteristic equation for T flip flop? Truth table.
Q is equal to T.
Yeah, T XOR Q. Yeah, T XOR Q. This is a characteristic equation of T flip flop. Okay, so T Q. What is the next step? You can say 0 0 0 1 1 0 or 1 1. So in the truth table, you can say the 0 0 1 1 0. Right? This is the truth table for T flip flop, and Q states the present state, and T Q n plus 1 is the next state. It is a Q n plus 1. Okay. So from the figure, you can say that T XOR Q. Otherwise, you can solve it from here also. Okay. Q n T XOR n plus 1. T XOR Q. So this is the following circuit implements the T flip flop only. Okay. Okay. So I hope all of you getting. So moving to the next question. So next question is the output Qn of a JK or SR flip flop is 0. Its output does not change when clock pulse is applied. Okay. Then the inputs Jn and Kn or Sn or Rn are respectively. So the output Qn of a JK flip flop is 0. Okay. First one, the output. Let's first read a JK flip flop. Qn, you can say it Qn dash of Qn is 1. J, K, and clock. Okay, so anyone of you can tell me what is the truth table for JK flip flop or SR flip flop? This is JM, truth table of JK. So from there we can see that its output does not change when the clock pulse is applied. So JN, KN, 2 n plus 1 next state. So this is a J 0 0 0 1 1 0 1 1. So what will be the output? 0, or you can also no change in the output when the inputs are 0 0 1 0 1, or if both inputs are 1, then it will toggle, right? And so what is saying, the output Qn of a JK flip flop is 0. Its output does not change when clock pulse is applied. Okay, when clock pulse is applied, the output does not change. So in which condition the output does not change? When the clock first, the Qn is 0, right? When we will apply to the clock pulse, that means whether the output input is 0 1, then it will be the 0, and whether the inputs are 1 0, then it will be 0. If clock pulse will be applied, then output will not change, okay, respectively. And in case of 1 1, it will toggle. Okay, from the excitation table you can also check, in case of 0 1 or 1 0, it will not change the output. So from the excitation table you can check also, or from here also. If already the output is 0, and then clock pulse is applied, in any case, if output is 0, then it will be the 0 only. If output is 1, then clock pulse applied, it will be the 1 only. Okay, so option C will be there, 0 x. So in x can be 0 or 1. Okay, 0 1 mostly. So from the excitation table also you can check. Okay, okay, okay. So in the question they are asking the output Qn, okay, of a JK flip flop is 0. Okay, the output does not change when clock pulse is applied. Okay, its output does not change when the clock pulse is applied. The input Jn and Kn are respectively, in which case the output will not change. What will be the input condition? That output will not change. Okay, so in case of 0 0, the output does not change, no change, it is written, it is either 0 or 1. Or in the case of 0 1 also, the output is reset, 0. In case of 0 1, it is also 0, right? So in the inputs, either 0, here it is given 0 and x can be a 0 or 1 also. Okay, and from the excitation table, if you will go to, from there you can also check. What will be the excitation table for a JK flip flop? Qn, Kn plus 1, J, K. So anyone want to answer for what is the excitation table for a JK flip flop?
J is Qn plus 1 and K is Qn plus 1 complement.
Yeah, that is a characteristic equation. Excitation table is Vishnu output and input. So it is a 0x,
0 don't care,
x,
1 don't.
yeah, 1 don't care now, and x 0. So it is asking its output does not change when the clock pulse is applied. That means when we are applying the clock pulse, in that case the output, whatever the input is there, does not change the output. It will be the same. So in which input condition it will not change. So from the here you can also check, or from here you can also check. In case of 0 0, the output will be the 0 x. X can be a don't care will be 0 or 1. Okay, are you getting? Yeah, I hope you understand. Okay, so moving to the next question. So the JK flip flop shown below is initially cleared. Okay, and then clocked for 5 pulses. The sequence at the Q output will be. So it is clocked for 5 pulses. Then what will be the sequence Q? The initially Q is 0, right? And Q dash will be 1. Okay. So in the JK flip flop, so it is 0 and it is 1 initially. Okay. Now K is 1. It is always set to the 1. Now J will change. J is connected to Q dash. So whatever value of Q dash, it will go on to J, right? Because it is connected to J. Okay. So first let's check that. Now in the first case, what is a J? J is 1 because initially Q is 0. It is clear, right? Then Q dash will be 1. So that means Q dash is connected to J. That means J is also equal to 1. And K is always set to 1. So K is also 1, right? So what will be Q? What is the value of Q in that case when J and K both are 1? Yeah, it can toggle or it can be 1. It can be 0 or it can be 1. So initially we are taking it is 1 because J and K both are 1, and in that case Q dash will be 0, right? Now Q dash will be 0, then J is equal to 0 and K is always set to 1, it is 1. Then what will be value of Q? J is 0 and K is 1.
0.
Yeah, 0. And Q dash will be 1. Now again Q dash is 1, then J is equal to 1 and K is equal to 1, right? Now this time what will be the output? Initially, first we have to also
1.
check the output also, right? So first it is 0, then it has gone to 1, then again the output is 0, and then again it is 1. Q dash will be the 0, again J is 0 and K is equal to 1, again what will be the output? 0. So 0 1 0 1 0. It will generate at for 5 pulses it will generate 0 1 0 1 0. For every pulse it will change like this, the inputs will change, and for 5 times period. So from the this sequence we can check it is just 0 1 0 1 0 1. Okay, so the sequence will be 0 1 0 1 0 1. So option D is the correct answer. Okay, just we need to try it right now. Initially Q is 0, then what will be the output for a 5 pulses? Q is 0, then Q dash will be 1, and Q dash is connected to J. K is always set to 1. Then we have to, you can here, so you can write the truth table of the JK flip-flop and just count, just check it, the output from here and write it down. Okay, for 5 times it will move like this. Okay, so I hope you have got. So we will move the next question. So next question is PLA contains option A and or array, option B NAND and or array, option C not and array, option D NOR and or array. What is the full form of PLA?
Programmable logic array.
Yeah, in the programmable logic array, what are the structure? So it has a programmable AND gate and programmable OR gate. Okay, that's why it is called programmable logic array. It contains programmable AND gate followed by programmable OR gate. This is a structure of a PLA. Okay, so it can contain the inputs. It can be anything X, Y, Z, A, B, C, and their complemented input is also available. So from there we have to make this circuit. For example, here AB dash is there, right? So for AB, for A, it is A, it is first line is A, it is A dash, again it is a B, it is a B dash, it is a C, and it is a C dash. So if we want to take AB dash, so just we need to cross mark it here A, then B dash. You will get the AB dash. Here 2 is connected. If one line is also connected, it is enough. Okay, just come here A, B dash. Here it is already connected to that one. Otherwise, we can also make it only one line and cross like this. Okay, and then if we want to find out the overall function, for example, F1 is called F1 AB dash plus B AC. So just we need to take these two and OR it. Okay, from this way we can make a Boolean function also. So this type of structure is called programmable logic array, and it has a programmable AND gate followed by programmable OR gate. So next one is a latch is an example of monostable multivibrator, or option B astable multivibrator, option C is bistable multivibrator, or option D 555 timer. So already we know that a latch is an example of bistable multivibrator because it has a two stable state, set and reset. A set state is denoted by a logic 1 and a reset state is represented by a logic 0. And because has a two stable state, that's why it is called a bistable multivibrator, because it has a two stable state. That is the reason it is called a bistable multivibrator. Okay, so moving to the next question. So next question is identify the circuit shown in the figure. It is option A positive edge trigger D flip flop where X is input, Y is clock and Q is output. And option B is negative edge triggered D flip flop where X is input, Y is clock and Q is output. Option C is positive S trigger D flip-flop where Y is input, X is clock and Q is output. And option D negative S trigger D flip-flop where Y is input, X is clock and Q is output. So from the figure, what we can see that uh, normally in the option it is given only it is a D flip-flop only. So it is a D flip-flop. Now we need to check what is the input, clock and output. So it is a mux. In the mux, this side already we know that this is the input side and this one is a selection line and this one is a output, right? So X is input in that case, and in the selection line we can give any pulse or clock also. So Y is clock and Q is output because it is given in output side. So now it is a D flip-flop and X is input, Y is clock and Q is output. Now we need to check whether it is a positive S triggered or a negative S triggered, right? So how we can check it? Anyone? So already know that what is a positive S trigger? This is a pulse, right? If pulse is going changing 0 to 1, it's a positive S trigger. It is a moving and the downward is a negative S trigger. Okay. So first let's assume that X and Y both are 0. Let or assume that X and Y both are 0. Okay. Now Y is 0. Then what will be the output of this mux? X is 0. So it is a 0. It is a 2 into 1 mux, right? When the selection line is 0, then it pass this 0 input to the output. If it is 1, then the 1 input is passed to the output, right? Okay, are you understanding? Okay, so first mux, let's uh, we can take any name. It is A. The output of the first mux is A. Okay, so output of first mux multiplexer we can say it. First mux output, or in brackets I am writing it A so that it is easy to understand, is 0 because X is 0, right? It is 0. Now here Y is given 0, so and then it is complemented to the next mux, so that means it is 1 for the next one, right? But in this time Q is unknown, we don't know, or we can say that it is 0. So in that case Q will produce, the Q is connected to 1. So if we initially assume that all the things are 0, so it will be 0 only, right? Now if we change the clock to 1, that means Y is 1. Now if change it to 1, then output Y is 0 right now also, so it is remains low because in that case that 1 will pass to the output, so again it remains low when we change Y is equal to 1. Now if Y is equal to 1, then A remains low, right? Or we can say that this latched, right? Are you getting? Again it is in a zero state, and here 0. Now all the marks, all the nodes are in state or initiated. It is 0, then it is 1, then it is 0. So whatever the output is there, it is passed to the this second max output, right? So now again bring it to the 0. The this figured is like this. Okay, first it is 0, then we have put it to the 1, then in that case remains 0. Again we are putting it y is equal to 0. Okay, so now what we can see that y is equal to 0, then what will be the a if we change? A is remains
0.
0. Yeah, a is remains to 0. First max output does not change. Now if we put x is equal to 1, if we take x is equal to 1, then what will be the output of first max?
A equals to 1.
Yeah, a is equal to 1, but for second max the 1, but it is 0, right? So output of the second mux does not change, right? The output of second mux does not change. Okay, so if we see that by toggling the clock, we will find that q follows x only. So whatever the x we are giving, that q is following, right? So in the D flip flop, what is the characteristic? Sorry, what is the truth table for D flip flop? D Q. So it is following the input. Already you know that. If D is 0, then output is 0. If D is 1, then output will be 1. Right? So from here we can see that the output of this is following the input. That's why it is called a D flip flop, and it is changes when the clock is moving 0 to 1. So that's why it is called positive edge triggered D flip flop. Okay. Yeah, Q is equal to D. Output follows the input. So, but from here we can see that when it is following, when the input is changed. So when x is 1, then q will be 1 for the next state. It is following that's why it is called positive edge triggered D flip flop. Have you get this? On every rising edge, it is following the input.
Ma'am,
Yeah.
ma'am, why? How we can say it is only a positive edge when we are changing from 1 to 0 also?
While changing 1 to 0, check that if it is changing the output, Q is changing or not. See, when we are changing X, then it is changing the output only, right? See,
Yes, ma'am.
and if we does not change the output, but in the negative edge trigger, it is not changing. Just go through that in this case, then you will able to understand. Here we can say X and Y both are 0, then first max output is 0, right? When we are changing X, then output final output is changing, otherwise it is remains low. Okay.
Okay, ma'am.
Yeah, we hope. Okay, so moving to the next question. So next question is, An SR latch is created using only two NOR gates, okay, with SR inputs feeding one NOR gate each. If both SR inputs are set to 1, the output will be option A, Q and Q dash both 1. Option B, no change in the circuit output. Option C, Q and Q dash both 0. And option D, Q and Q dash complementary to each other. So what will be the answer? So SR latch is created using only two NOR gates. Okay, here two NOR gates and one input of NOR gate is given to S and R, and others output is connected to the one input in the cross connection form. If both the and R both are set to 1, then what will be the output? So already from the truth table we know that it has gone to the indeterminate mode. That means can't invalid. So when S is equal to 1 and R is equal to 1, then what will be the output? Q 1 1. Let's first assume that Q1 Q is 1 and Q dash will be 0, right? So in that case 1 0, what will be the output? Is 1, right? But R is equal to 1, Q, what will be the Q? 0 and Q dash will be 1. So when S and R both are 1, so Q dash, Q and Q dash both are going to equal to 0. That's why it is on to indeterminate mode or invalid state. This is a limitation of SR latch. So option C is the correct answer in that case. Q and Q dash both are 0. That's why it is invalid state. Okay. So now moving to the next question. Serial inputs are applied in the following manner to the J and K flip-flop and through AND gates as shown in the figure. What would be the resulting serial data that would be present at the output Q? We need to find out the output Q. There is one clock pulse for each bit time. Assume that Q is initially 0 and present and clear signals are preset and clear signals are always high. The input bits are applied from left to right. That means this side to this side. So initially Q is 0, right? Initially Q is set to be 0. Now ABC is applied to J and XYZ applied to K. Okay, and it. So let's first J and K. What would be the output? We need to find out the output. So anyone of first we need to write truth table so that we can write it clearly. So can anyone of you let me know what will be the truth table for JK flip-flop? 0 0 0 1 1 0 1 1. It is 0 first, that means no change. Whatever state is there, there will be no change, and is 0 1, and it is a toggle, right? Yeah. So in the J, let's say A, B, C. First, we will check this one. 1, 0, 1. So I'm writing it as 1, 0, 1. What will be the output of that AND gate? Will be 0, right? 1 into 0, 0, 0 into 1, 0. Right? So final will be 0. can write it more clearly. So J is A, B, C. So 1, 0, 1. It is ANDed, so you will get 0, right? Similarly, in the K, X, Y and Z are ANDed. So I am taking from this side. So 0, 1, 1. 0, 1, 1. What we will get? 0 final, right? So that means J is 0, K is 0. What will be the output? 0, because it is initially set to 0. So no change. So it will 0, right? Now next to the next bit. Again clock is applied to move to the next bit. So it is 0, 1, 1. What we will get? 0 only. 0 and 0. 0 and 1 is 0, 0. Next K, 0, 1, 0. Again we will get 0 only, right? Again 0, 0. So output will be no change. It is 0. Now move to the next bit. It is triple one. So triple one, if we AND the triple one, we will get 1. And for K, what is it? 0, 0, 1. 0, 0, 1. We will get finally 0. Right? So what is the output in that case? 1, 0. J is 1, K is 0. What will be the output? Anyone of you want to answer this question? J is 1, K is 0. Yeah, right. 1. From the truth table, we can see that 1, 0, the output is 1. Okay, so now moving to the next bit. Next bit 0, 1, 1. So 0, 1, 1 is ANDed. We will get final 0. Now next, fourth one, right? 1, 1, 0. 1, 1, 0. We will get final 0 for K. Draw a line so that. So again it is 0, 0. What we will get? 0 or 1. Because whatever the output is stored, that will no change condition. So again it will be 1 only, because if it is in the previous, it is in the memory, it is stored 1, so it will be 1 only. Okay, have you get? Yeah, no change, right? Also no change, so output will be 1 only. Now moving to the next bit. Next bit is 0, 0, 0. 0, 0, 0 and at 0. Again it is triple one. So we will get 1 if we AND it. So now next one is 0, 1. So J is 0, K is 1. What will be the output? Now 0. That no change will be changed. So the output has gone to 0. Yeah, 0. Now moving to the next bit. So 1, 1, 0. 1, 1, 0. Final J will get 0. Now next 1, 0, 0. Right. 1, 1, 0, 1, 0, 0. Again we will get 0. So J is 0, K is 0. Again no change. So output is 0. So 0. Now last one 1, 0, 0, 0 only, and 0, 0, 1. It is 0. So again J and K both are 0. So no change in the output. So it is again 0. So what output we have got finally? 0, 0, 1, 1, 0, 0, 0. This is a Q. So let's match to the answers. 0, 0, 1. Option A, right? Yeah. Anyone want to ask anything? Yeah. Okay, so final answer is 001100. Option A is the correct answer in that case. Okay, okay, so I hope you understand this. Moving to the next one. Okay. So next question is, consider 1 into 4 demultiplexer circuit shown below. What would be the output bit for the input condition? S is 0 and S0 is 1 and S1 is 1. Both are 1. Yeah. Now if preset and clear are given as 0, then output will change. If preset and clear is 0, that is the different case. In that case, the flip-flops are not active. Okay, because preset and clear we are giving to clear out all the stored bit. It is always high only. It cannot be a 0. If it is 0, in that case for every clock it will change. I mean it will clear the output. It will always be 0. In the next week onwards, you will see the counters and register circuit. So you will able to see the preset and clear is always in high, not in 0. Okay. Yeah. Okay. So moving to the, so already all of you I think know that what is the truth table for DMUX. T in is given, right? So for a particular selection line, whatever the input is there, that will reflected to the corresponding output. If it is a 0 0, Sn and S0. It is a Y0, Y1, Y2, Y3. So 0 0. There is a 4 possible combinations for selection line. 0 1, 1 0, 1 1. Right? If both are S0 and S1 is 0, so whatever the input is given, it is goes to the Y0, right? If it is a 0 1, then the whatever input is there, it will pass to the Y1, and in case of 1 0, it will goes to Y2, and if both are 1, then it will goes whatever input is given goes to the Y3, and all other outputs are in that case 0. So in case of 0 0, D in is 1, so Y0 will be 1 and all other outputs will be 0. And if it is 0 1, then 1 will be 1 because D in is given to 1, 0, and all other outputs will perform act as a 0. And in case of 1 0, 0 0, Y2 will be high and all other output is low. And in case of 1 1, it is 0 0 0, Y3 will be high and all other output will be 0. So from here it is given S0 and S1 are both are high. So Y3 will be 1 and Y0 is 0, Y1 is 0 and Y2 will be 0. So let's check from the answers from the option. Y0 is 0, Y1 no, Y1 is not 1, and here y0 is 0, y1 is 0, y2 is 0, y3 will be high. Option B is the correct answer. Okay. Okay, so I hope all of you getting. Okay, so moving to the next question. So next question is identify the PLA circuit shown in the figure. So how we can
Y2 is 1, ma'am.
what?
In
Yeah.
before question.
Okay. Before question. Yes. Huh. What you want? What you are asking?
Ma'am, it is given that. Okay, ma'am. Okay, ma'am.
D
Sorry.
in
I thought
is
0,
right.
1.
Yeah. Okay. Have you got this question?
Okay, ma'am.
Yeah. Okay. So identify the PLA circuit shown in the figure. So here already A is given, B, C, and there complemented is also available. Okay. A, it is a and it is on this side is A dash. Similarly, B, B dash, C, C dash. It is given to the end and then OR gate. So now we have to check what function X and Y are going to implement. So first we can check for X. So X. First we need to find out these AND gates output. So just leave that because it is given all are crossed. So from here we can check what will be the output of this AND gate. Can anyone answer this? Already told you it is a programmable AND gate followed by programmable OR gate, right? If it is crossed this type, that means that output, that will be the input is given and that ended to the output. Okay. So this is a dash, A dash, then B dash, and this one is C, right? A dash, B dash, C. Yeah, sum of product form. Now, what is what will be the output of this NAND gate? AND gate. This is a dash, B, right? A dash, B, and C dash. Now next, we have to check for this AND gate. So it is a dash, B, A dash, B, and C, right? A dash, B, and C. Now check for next one. A, B dash, C dash. A, B dash, C dash. It is A only. A, B dash, C dash. Now next one. A, B dash, C. A, B dash, C for this AND gate. And for this AND gate, A, B, C dash. A, B, C dash. We need to check where it is crossed only and then and T is inputs. So it is A, this one is A dash, it is B, B dash, C, C dash. So it is crossed to A and here it is B and it is crossed to C dash. So A, B, C dash and these three inputs. Similarly for this AND gate, A, B, C, A, B, C, right? Now we have to check again for OR. Okay,
Ma'am, what will be for the first AND gate?
it it is crossed at all. So A dash, B, B dash, C, C dash. So that will be the zero
Zero.
only. Yeah, it's
Okay.
zero only. So you can skip
But
it.
why it is given, ma'am?
It is given just showing that it is a question, so they can give it like that. So just you need to check where it is crossed. If it is crossed at this, so that will be the zero only. If it all are crossed,
Okay, ma'am. Okay.
if you finally calculate that, that doesn't matter. Okay, now or where it is crossed. So this one. So first one is A dash. B dash C, right? Because for this one and for here it is dot here, so plus because it is all, so we have to add all where it is got A dash B C dash, right? And now add this one A B dash C dash. Now check to the another one, last one. It is a ABC. So A B C. So first we need to find out what will be the value of this one. It is 001, right? 001. A dash B dash, if we are taking 01 form, and it is represented as 0 1 0. It is 1 0 0. It is triple one. So if we want to write in terms of min terms, so what will be the values? It is a 1, it is 2, it is 4, and it is 7, right? X, it is X. Now check for Y. Now Y
Ma'am,
is,
it's Y, ma'am.
this one is for X, right? Yeah, what, yeah. Now for Y we are going to calculate. So for Y, we can write it A dash B C, because here it is first, then next one is A B dash C, right? Plus A B C dash for this one, for last one. It is A B C. Again, we can write it in order to find out what will be the min terms or what will be the value. So A dash is 0 1 1. It is 0 1 0. It is 1 1 0, and it is triple one. So what will be the min terms value? It is 3, right? And it is 0 1 2. So first you can write 2 and 3. It is 4 2 6 6 7, right? 2 7 9. Sorry, it is, I have written it is the opposite. It is 1 0 1 equal to the 5 only. Just a minute. It is 3, it is 5, correct, right? So now we can see that, have you understand what is a min term expression for? It is for, or otherwise we need to solve it by K map or any other. You can solve it anyway. So first x and y values we have got in terms of min terms as well as Boolean expression. So first check what are the options. So option A is full binary full adder, where x is some output and y is carry output. Option B is binary full adder, y is some output, x is carry output. Option C is binary full subtractor, where x is difference output and y is borrow output. Option D is binary full subtractor, where y is difference output and x is borrow output. So from the min terms or here, you can check that the, what is it? For binary adder, what will be the min terms for binary adder? If you remember that it is a 1 2 4 7 for sum, and for carry the min terms are 3 5 6 7. So it is a full adder, binary full adder, where x is some output 1 2 4 7, and y is carry output 3 5 6 7. So option A is the correct answer. So you can, there are other ways, or ways are also from there you can also check, solve it. Otherwise you can directly solve it here, or you can check it from min terms, because you have to remember all the min terms related to half adder, full adder, full subtractor and half subtractor also, so that you can directly write it down. Okay, so I hope all of you getting. Are you getting? It is clear. See how we can solve this type of question. Just we need to find out the final expression. Okay, so I hope all of you are getting. So moving to the next question. So next question is, a positive S trigger D flip-flop is connected as shown in the figure below. Okay, so what would be the Q output in relation to the clock? Assume initially Q is 0. Initially Q is 0. So Q dash will be 1. The clock is given like this. We have to find out the output in terms of waveform in relation with clock. So this one is clock, we need to check it. Then what will be the output? So initially Q is 0, Q dash will be 1 and Q dash will be 1. Then D is 1, right? The truth table of D flip-flop. Truth table. D is 0, out D and output. If D is 0, output is 0. If D is 1, output is 1. Right? Already we know that. So that means Q dash is 1. So Q dash is connected to D. That means it is also 1. When clock is applied, so when we are starting from here, so D is 1 when clock is right, output is also 1, Q is 1 because D is 1. For D flip-flop, the output follows the input, right? Already we know that. That means Q is also 1. So Q is also 1 and Q dash will be 0 for this clock, right? So it is 1. Again, this is for 1 clock. Okay. Now Q dash is 0. So again D is 0 for next clock. D is 0, then output will be 0. Okay. So it has gone to down. Again, what will happen? Q is 0, then Q dash will be 1 and D is 1. Right? So for next clock it is 0. So then again it will go up, then down. So it will follow like this. Have you understand this question? Yeah, are you getting? This is a clock signal, right? It is going up, down, up, down. This is the one cycle, right? This is a total one cycle. So initially Q is 0. Okay, initially Q is 0, then Q dash will be 1, right? Q dash will be 1. So if Q dash is 1, then D is also 1. In that case, D is 1. Then it will goes to high. The D is 1, then Q is 1 because the output follows the input. If D is 1, then again Q has gone to 0. Then it will 0. So for one cycle it is high. For next cycle it is 0. For again next cycle it is 1. Then again it will be 0 only. Okay. So from here, option D is the correct one. Timing diagram D. Okay. So it is a Q output relation with clock. Okay. This is the output relation with clock. So I hope you have you are getting. So moving to the next question. So next question is, in a demultiplexer, the number of output lines is n. Output lines are n, and the number of selection lines is m. Selection lines are m. So which of the following is correct? Yeah. So in the demultiplexer already we know that there is only one input and number of output is based on the number of selection lines. Okay. So if number of selection lines are m, then total output will be the number of output lines are 2 to the power m, 2 to the power selection lines. For example, if selection line is 2, m is equal to 2, then n is equal to 2 to the power 2, 4. That means number of output lines will be 4. Okay. So 2 to the n is equal to, here it is n is output line and m is a selection line. 2 to the this correct relation is correct, not this one. N is equal to 2 to the power m. Yeah, option 1 is correct one. Okay, so moving to the next question. So next question is, a programmable logic array PLA is shown in the figure. The Boolean function f is implemented. So from the options, which option is correct? So let's take it. Which Boolean function f is implemented? So first it is a check for the AND gates. So what will be the, I am writing it here only. So what will be the output of this AND gate? So where it is tossed, we have to AND these points. So P dash, Q dash and R. P dash, Q dash and R is the output of first AND gate. Now what will be the output of the next AND gate? It is a P dash Q R. I'm writing it here. P dash Q R. Right? Q R. Now what will be the output of this AND gate? This is a P Q dash R. Right? And now we need to OR these output of the AND gate. So first one is P dash Q dash R plus it, because it is OR, P dash Q R plus P Q dash R. Right? Now match to the answer. P dash Q dash R, P dash Q R plus P Q R dash. So option 3 is the correct answer. Okay. So I hope all of you getting this question. So moving to the next one. So next question is also based on the PLA only. So determine the output of a logic array given in the following figure. The axis represents connected link. That means cross is represented the connected link. So we need to check final output F. So where it is, first we need to check the AND gate, output of the AND gate. So first one is A, B, right? A, B. for first AND gate. Now next one is A B dash. A B dash for the second AND gate, and A dash B for the third AND gate, and the final gate and fourth one A dash B dash. A dash B dash. Now we have to OR, sorry, it is AND. Here it is ANDed, right? So just, so again we have to AND these. So first one is A B dash, because here it is not a OR, it is a AND. So we have to check for that also. A dash B. If we AND all those, so A dash B B dash, so that will be 0, because A dash will be cancelled out and B dash is also cancelled out. The final output F is 0. So option 3 is the correct answer. Yeah, 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 no, it is a 0. Answer is 0. So yeah, moving to the next question. The next question is the minimum number of and OR gate required for the implementation of Boolean function. So here two Boolean functions are given, which min terms are given. We need to first implement the PLA and check how many and OR gates are required for this Boolean function implementation. So how we can check it? In order to find out the minimum number of AND gates and OR gates, so first we have to find out the what will be the Boolean function or Boolean expression for these two functions. How we can find out? Using K-map, or because we have to minimize that one, and then we have to check number of AND gates and OR gates. Okay, so let's assume that I'm giving some name. It is y1 and this one is y2. Let's assume that, because we have to minimize for these two terms. So min terms are given, so we need to find out the Boolean function. So for y1, the K map is, if there are three terms, so A, B, C, right? It is a 0 0 0 1 1 1 1 0 0 1. Already you know that. So it is given 0 1 3. So it is a 0 0 0 0 1 0 1 1 0 1 0. So it is a 0 first row, first, this first cell is 0, right? So it is given, it is 1 and it is also 1. So 0 1 2 3. So 3, the 3 number of, in this cell the value is 1, right? Now 6 and 7 we have to, so 0 1 2 3 4 5 6 7. So 6 and 7, it is for y1. I'm assuming for this one. Okay, so let's group it. Okay, right? So that can be multifunction also if we make this type also. So you can take any of it. So final and number of and or will be the same only. So y1, what will be the Boolean function for y1? So it is a dash, and what will be the common? B dash, right? Plus here a b c, plus here a, common is b, the common is 1, so b only. Okay, a dash b dash bc plus ab. Now similarly we need to find out for y2 also. A B C 0 1 0, 0, 0, 1, 1, 1, 1, 0. So what are the min terms? 3, 5, 6, 7. So 0, 1, 2, 3, 3, 4, 5, 5, 6 and 7. Again we need to find out. So y2 is equal to a, and here 1 is common, so that means c. Here again a. So here 1 is common, that means b. Here again b, c. So now plus means or, right? And these are the literals, which means AND gates. So first we will check what are the terms. Some terms are here common, AB and BC, because we are going to implement the program PLA circuit, right? We're using PLA because it is given. We have to implement using PLA and then find out number of AND gates and OR gates. Otherwise we can already, because AB and BC here it is common, so we have to make only one AND gate. So 1, 2, 3, 4 AND gates, and number of OR gates, two functions are two outputs are given, so that means two OR gates. So we can implement also. So let's wait, I can implement. Okay, so A, B, because three literals are given. A, B, C. So this is a B bar. Here it is a C, and this one is, this one is C dash, right? So now and it. So first here two literals are common, right? AC, BC and AB are in both, so we can take it 1 as it. So first I'm taking it AC. So A and C. A, C. Output of this AND gate is AC. Now next one is AB, right? So A, B, AB. Now next one is B, C. So B and C. Now last one is, now AC is covered, AB and BC is covered. This. Now what left? A dash, B dash. So B dash is there, sorry, B dash is there, and just I'm connecting it here from here. So A dash, B dash. Okay. So we have to implement two functions. So we have to OR it. Here y1, I'm giving it the y1. So what are the functions of y1? A dash, B dash, A dash, B dash, BC, A, B. Now for the second one, I think I can OR it here. So AC, AB and BC for y2. So number of AND gates we have got 4, and number of OR gates are 2. So 4 AND gates and 2 OR gates. Okay. So we can check it from here directly. Just whatever the common in both the Boolean expression, just take it as a 1 and then count it, the number of literals. Okay. And already we know that two functions are there, so we can implement by 2 OR gate only. Otherwise you can directly implement the PLA circuit and take it from there. there is no need to again make a BC bar and AB bar, then the circuit will be confused. When we need to take the this BC and AB and here. So whatever common in these two functions, just take it as a one. Okay. So I hope you understand this question. So moving to the next question. Okay. So a flip-flop circuit can be used for counting, scaling, demodulation, or option 4 is both 1 and 2. So anyone of you want to answer this question? Already we know that a flip-flop is a basic digital circuit which can store only one bit. So that can be used for counting purpose, because if we connect a number of flip-flops in a series, then we can store the number of bits. If, for example, if we are cascading the 4 flip-flop, then that can store the 4 bits, and that can be used for counting a 4-bit number. Okay, 4-bit also, like this. And scaling, and flip-flop also used for the frequency division. So I think now I didn't cover that question. However, you can able to see the flip-flop is also used for scaling the input frequency. Okay. Demodulation is the another concept. Demodulation used for extract the original information. So that is not using the flip-flop. Okay. So flip-flop used only two for in this purpose only. So option 4 is the correct answer. Both 1 and 2. Flip-flop can be used for counting and scaling purpose only. Okay, not a
Ma'am, what is the meaning of scaling?
scaling means we can divide the frequency, or we can, I mean, extend the number of bits. For example, you are giving the clock signal, right? So that has some frequency you are giving. Okay, that can have. We can use the flip flop by dividing that input frequency or multiplying this input frequency. I have one example in the, I think, the next few slides, then you are able to understand in that case. Okay, so flip flop also used for scaling purpose, in scaling input frequency also. Okay, scaling means increasing or decreasing the frequency, or you can amplify or increase or decrease the any value or any quantity. For example, if we are here using the number of flip-flops in series or parallel, that means also we are scaling, or we are increasing the number of bits also, that is also called a scaling also, right? Scaling means increasing or decreasing the value, any value. Have you understand? Yeah, hello. Are you getting?
Yes, ma'am. It will be always by 2, 4, 8, like that.
Yeah, 248, like that only. Okay, so moving to the next question. Which condition is shown JK flip-flop as no change next state from the present state? Which condition is the shown in the JK flip-flop as no changes next state from the present state? So when J and K both are 0, or J is equal to 0, K is equal to 1, or option 3, J is equal to 1, K is equal to 0, and option 4, J and K both are 1. So already we are familiar with the truth table of a JK flip-flop. So when J and K both are 0, then the next state will not change. That represents the no change state. Okay, from the present state. Whatever the present output is there, for the next state, that output will be the same. So for j and k both are, when both are 0, then that represents the no change state. So option 1 is the correct answer for this question. Okay. So moving to the next question. D flip flop can be made from a JK flip flop by making J is equal to K. Option 2 is J and K both are 1. Option 3, J is equal to 0, K is equal to 1. Or option 4 is J is equal to K dash. So yeah, anyone of you want to answer this question? Then I will go through the answer. Yeah, option 4 is the correct answer. J is equal to K dash. So this is a question related to conversion of the flip-flop. So it is D flip-flop can be made from JK flip-flop. So that means JK to D conversion. Okay, because we are making a D flip-flop using a JK flip-flop, right? So for this conversion, already we know that we have to make a characteristic table from the excitation table. Already we know that D Qn, this is the present state, and Qn plus 1, this is a table for D flip flop 0, 1, 1, 0, 1, 1. So whenever the D is 0, so output of the next will be the 0 only, and when D is 1, then output is also 1. We already know that the output of a D flip flop following the input. So from J and K flip flop we have to make a D flip flop. So from the excitation table we can take it. So for 0 0 it is, we know that 0x 0 cross, then cross 1, 1 cross, cross 0. Okay. Now we need to find out the value of J. What will be the value of J in terms of D, and what will be the value of K in terms of D, right? So for that we have to make a K map. D, sorry, it is only so D and Q1, because we need to find out the value, what will be the value of J in terms of D, and what will be the value of K in terms of D and Q1. So 0 1 0 1. So when it is 0 0, so it is 0 0 1. So 0 1, it will be the cross, then 1 cross. So in terms of J, what will be the value? J is equal to D, and it is the K map for K. So D Q1 0 1 0 1. So at 0 0 it is a cross, at 0 1 it is 1, and at 1 0 it is cross, and here it is a 0. So K is equal to D dash. Okay. So J is equal to D and K is equal to D dash. So from here we can also say that J is equal to K dash, because Q and dash, this is J K, right? For K dash it is JK to D flip flop conversion. Here input is JK, we are converting the J and K to the D flip flop. So J is equal to D, K is equal to D bar, right? J is equal to D and K is equal to D bar. From here we can, it is also equal to D is equal to K bar. So from here we can write as J is equal to K dash, right? So from here, option 4 is the correct answer. Okay, I hope all of you are getting. If you have any confusion or doubt, you can ask. Otherwise, we can move to the next question. Yeah. Next question is, which of the following logic circuits don't have no change condition? Don't have a no change condition. In D flip flop, or option 2 is T flip flop, in option 3 JK flip flop, and option 4 is SR flip flop. Yeah, in D flip flop circuits, we don't have a no change condition, and all other flip flops we have a no change condition. For example, in the JK flip flop, we have seen that at 0 0 there is a no change condition, and similarly in the SR flip flop also there is a no change condition, and T flip flop also have a no change condition. But in a D flip flop, whatever the input we are giving, that will be the reflected to the output. For example, if input is D is equal to 0, then output will be the 0, and if D is equal to 1, then output will be the 1. So this is the only flip flop that don't have any no change condition. So D flip flop however don't have any no change condition. Okay. So option 1 is the correct answer for this question. Okay. So yeah, moving to the next question. Yeah, I am talking about this question. In this question, you will get to know what is the scaling or frequency scaling. Okay. So if input to a T flip flop is a 200 hertz signal, so already till now we have seen that we are normally giving a clock signal, right? What is this clock? This clock is a this pulse, so it must have some frequency, right? Without frequency we can't give, and in the J and K we are giving the discrete values, either 0 or 1, but in the clock we are giving the pulses, positive is triggered or negative is triggered. So that clock must have some frequency, right? So if we go through the deeper, then we will able to know what is this frequency here. This question is related to this clock frequency, and in the flip flop it is also a considerable amount of, when the frequency will changes, what will be the output frequency, the question will be asked at that also. Okay, so we will solve this question. Yeah, yeah, 12.5 is the correct answer. Let let me solve this question, I hope. So already it is given, if the input T flip flop is a 200 hertz signal, then what will be the output signal frequency if 4 T flip flop are connected in cascade? That means it is a clock frequency here, 200 hertz signal is given. If we cascaded the 4 T flip flop, what will be the output, F output of this signal frequency? Okay, so we need to find out what will be the output frequency of these 4 T flip flops. Okay, so I'm just making it with a clock, or we can say that input frequency. Now it is a Q, and this one is a Q dash. Okay, so the input frequency is like this. This is a clock pulse having 200 hertz frequency, and in one of the previous question, I think we have seen that the, just a minute, here what will be the output? Here it is a one cycle, right? clock signal is given, the what will be the output clock cycle? It is whole, so it is f by 2, right? It is f, and then it is a f by 2, right? Because it is a half of, it is a 2, then it is a 1 cycle. When the clock signal has a 2 cycles, then it has only 1 cycle, right? So from here we can see that the, if we have input frequency, then f by 2 at the output frequency. Okay, right? I hope you are getting what I am trying to understand you. So from there we can make it like this. Input frequency is f, then output frequency will be f by 2. Okay, so from here we can get it, f output frequency, this is the input frequency. This is a formula, you can remember it, to the 2 to the power n, where n is the number of flip flops. Okay, so from here we can get f output frequency, f input frequency is given 200 hertz, already given. So 200 hertz divided by 2 to the power n. Here n, it is already given 4 T flip-flops are connected in cascade. Here n is the number of flip-flops which is given equal to 4. Okay. So 200 divided by 2 to the power 4. So 200 divided by 16. If you calculate it, you will get 12.5 hertz. Okay. So in the options, if you see that there is no option, none of the above will be there. It is hertz to 12.5 hertz. Okay, this is a formula in order to find out the what will be the output frequency of any flip flop. If input frequency is given, you can find it out the output frequency. Yeah, this is example of scaling. This is called scaling. Okay, the flip flops can be used for scaling the frequencies. This is the example of scaling. Here we can see that the input frequency is given 200 Hz, but at the output, when we are connecting the multiple flip-flops in a cascade, we are getting the output frequency by 2 to the power n scale version. Or we can say that we are decreasing the frequency. Okay, so moving, I hope you have understand this question. So moving to the next question. So next question is, which of the following is true? Option 1, a flip-flop and latch both function same. Option 2, flip-flop is edge triggered and latch is level triggered. Option C is flip-flop is level triggered and latch is edge triggered. And option 4 is either a flip-flop and latch is a combinational circuit. So either flip-flop or latch is not a combinational circuit. Option 4 is wrong. And flip-flop and latch both function same. No, flip-flop are made using latch. Okay, so latch is only one stage, but flip-flop we are connecting the two stages of the latches. So flip-flops are made using latches. So flip-flop output changes when clock is applied, while latches continuously changes when input output changes. Okay, so option 2 is the correct answer. Flip-flop is the edge triggered and while latches is the level triggered. Whenever we are giving the pulse, it changes the input output. So flip-flops are edge triggered and latches are the level triggered. Okay, so these are the some questions for this week video lecture based on the. So if you have any doubt, you can ask. Otherwise, we can close this session. Yeah. Thank you everyone. Thank you for joining. Now, if you have any doubt, you can ask the question. Otherwise, we can close the session. Yeah. Thank you everyone. Thank you for joining the session. Okay, you can leave now.